Assalamualaikum and good day. In this topic, we will derive or develop an overall rate law equation based on the mechanism of reaction and the rate limiting step. Okay, what is the rate limiting step? Okay, at steady state, the rate of adsorption, surface reaction, and rate of desorption are equal to one another. Therefore, negative R apostrophe C, so negative R apostrophe is the overall net rate equation or net rate law equation for the catalytic reaction, and is equal to rate of adsorption, also equal to the rate of surface reaction, also equal to the rate of desorption. But before that, we need to know which steps of reaction is rate limiting or rate controlling, and it is based on the particular step in the series of reaction. So we will derive the overall rate equation based on the adsorption step, surface reaction step, and desorption step. Alright, so in developing the step limiting for the overall rate of reaction, we will use Lamuir-Hischel-Wood approach. Okay, first, assuming a sequence of steps in the reaction. Again, we need to assume the steps of the reaction for adsorption step, surface reaction step, and desorption step. Okay, based on these three steps, we will write the mechanism for each step. Okay, for example, in adsorption step, the mechanism is either as molecular or atomic adsorption. Whereas for surface reaction, it is either single or dual side mechanism, or it can be irradial mechanism. Then the third step, by assuming all steps are reversible for adsorption and desorption, and it also can be irreversible or reversible for surface reaction, we will write the rate law for the individual steps. Then postulate the rate limiting steps, either adsorption step, surface reaction, or desorption, controlling the overall reaction. Steps that are not rate limiting are used to eliminate all coverage dependent terms. Okay, what is coverage dependent terms? Coverage dependent terms is the term for the concentration of species that attach with active site of catalyst. So all term that we write it as CI.S. Okay, for example, CA.S, CB.S. So we want to eliminate all those terms. And also CV, concentration of vacant site term. Okay, there is no accumulation of reacting species on the surface. Therefore, the rates of each step in the sequence are all equal. And the last statement, CV or C.S or CI.S in the rate law must replace with measurable quantities. So remember this statement, CV or concentration of all species that attach with S must be replaced with measurable quantities. Okay, then if you know which steps are the rate limiting for the reaction, so we can assume that, so the adsorption, if the reaction is adsorption rate limiting, Ka, rate constant for adsorption, will be smaller than Ks and Kd. Okay, so this is for the case if adsorption rate limiting. So the first equation. But if the surface reaction is rate limiting, Ks will be smaller than Ka and Kd. And if desorption is rate limiting, Kd smaller than Ka and Ks. Ka here is adsorption rate or rate constant for adsorption step. Ks rate constant for surface reaction. Kd rate constant for desorption. So either one. We will use either one based on which step is the rate limiting steps for the overall reaction. So for this one, I will explain it later. Okay, then this is the example for the addition of inerts in catalytic reaction. Okay, let's say for the reaction of A to B, and stated in the question that the surface reaction is rate limiting. So the mechanism of reaction given as A plus S, reversible reaction A dot S. So the first step of reaction is the adsorption reaction. Then the second step, if you look at the mechanism, A dot S, irreversible reaction to produce B dot S. So the second step is surface reaction step. Then next step, B dot S, desorption reaction. Okay, via reversible reaction will produce B plus S. So first you look at the overall equation, rate equation A to produce B. How it's occur? So the based on the mechanism of reaction, step by step. So the first step is adsorption, second step surface reaction, the third step desorption reaction, and the last step, because the reaction involves the addition of inerts. So in this case, inerts will attach with surface reaction, active surface to produce I dot S. So in this case, bermaksud the reaction is for adsorption of inert. So meaning that you have two adsorption step. First, for the adsorption of A, the second one for the adsorption of inert I. Okay, then derive the rate law based on the assumption that the surface reaction rate is limiting. So you will get the rate law as the equation in the table, yellow table. Okay, light yellow table. Okay, so yang ni saya nak explain how we can simplify the equation if we have certain assumption. Okay, let's say the first rate law, you tengok denominator dia quite long. So denominator of the equation is 1 plus KAPA plus KBPB plus KIPI. How to derive this rate law? So I will show it in another example video. Okay. So how to simplify the equation kalau diberi another assumption. So in this example, okay, if KIPI larger than 1 and also larger than KA and Kb. For this case, if the concentration of inerts that used in the reaction is too large, okay? So because of too large inerts in the reaction, therefore the concentration of inerts is too high. Then because of that, KIPI will be larger than other denominator. So we can simplify the equation by eliminating KAPA, KBPB, and 1. So the rate law becomes the equation in the pink table. The rate is reduced by species I. It shows that the inert can strongly inhibit the reaction of A. So the function of inerts in the reaction is it will block the sites on which A must adsorb to react and lowers its coverage to a small value. Therefore, inhibit the reaction. So inerts ni actually a catalyst, a type of catalyst but in negative function. So that's all about the rate limiting.